Assalamualaikum and good day everyone. In this video, I will explain about the fourth order Runge-Kutta method. This method was developed by German mathematician Carl Runge and Martin Wilhelm Kutta. Actually, under Runge-Kutta method, there are another two methods. The second order Runge-Kutta and also the fourth order Runge-Kutta. But the fourth order RUNGE-KUTTA is the most popular RUNGE-KUTTA method. For the purpose of this video, the second order RUNGE-KUTTA method will not be discussed. In general, the RUNGE-KUTTA method is the derivative-free method. It does not require the computation of higher order derivative. For the sake of simplicity, I will call this method as RK4. Okay, suppose now we want to solve the ordinary differential equation dy over dx, and we know that this dy over dx can be represented as f of xy, and given the initial condition y of x naught equals to y naught, and now we want to solve this ordinary differential equation by using RK4 method. Solving this equation means you need to find the y and the x value. So the RK4 method states that to solve this ordinary differential equation, your y value, the approximation of y value is equals to yi plus h over 6 k1 plus 2k2 plus 2k3 plus k4. And the approximation of x value is equals to xi plus with h, and the h value is the step size or the gap of interval. From these two formulas here, you need to know the values of k1, k2, k3 and also k4. So k1 formula is f of xi yi. K2 is equals to f of xi plus half h yi plus half k1h, and k3 equals to f of xi plus half h yi plus half k2h, and the k4 value is f of xi plus h yi plus k3h. That's it. These are the formulas to solve the ordinary differential equation by using fourth order Runge-Kutta method. The derivation of this formula will not be shown in this video. Okay, and don't worry, you don't need to memorize this formula. This formula is given in your exam. Okay, next we will look at a few examples. For example 1, compute the approximate solution of the following ordinary differential equation that satisfy the initial condition y0 equals to 2 for x more than 0 less than 2 by using fourth order Runge-Kutta method with a step size of 0.5. So this is an ODE problem, the initial value problem, because we have one initial condition, y0 equals to 2, and this 0 is your x0, and this 2 is your y0. Okay, and from this formula, the step size is 0.5, so h equals to 0.5. And this question asks you to use RK4 method. And so, we know that the formula for RK4 is given by this formula here. We need to find the approximate solution of x and y. And we know that from the question, the range of x values from 0 until 2. And we know that the x0, the initial condition, is at 0. So, x0 equals to 0. x1 equals to, since the step size is 0.5, so the x values increase by 0.5. So x1 is 0.5, 0 plus 0.5 is 0.5, x2 is 1, x3 is 1.5, x4 is 2. And we stop until here, because our range for x only until 2. So these 4 values of x are the approximate solution of x values. So for y values, also we need to have 4 y values. So we must do 4 iterations to find the y values. And besides, actually, this x value here I got from the formula of this. Xi plus 1 equals to xi plus h. Alright? So we need to have 4 iterations to find the approximate solution of y. So we need to find the y1, y2, y3, and also y4. Okay, for the first iteration, our x1 is 0.5. And to find the y1, the formula is given by y0, y0 plus h over 6, k1 plus 2k2 plus 2k3 plus with k4. So to find the y1 value, we need to find the k1, k2, k3 until k4. And k1 is equals to f of xi, yi. So for the first iteration, it is f of x0, y0. So f of x0, so our x0 is 0, y0 is 2. So f of 0 and 2 is actually, you just substitute 0 and 2 into the f function. So our f function is this one, the dy over dx. So f of xy is exponent of negative x minus 2y. Okay. Okay, for k1, f of 0 and 2. So exponent of negative 2 minus 2 times 2. So you just use your calculator. And the answer is negative. Oh, sorry. This one is supposed to be 0. Because negative x is 0. So 0 here. And the answer is negative 3. So this negative 3 is the k1 value. Okay, next, you need to find the k2 value. So the formula for k2 is f of x0 plus half h, comma, y0 plus half k1h. So f of, and we know that x0 is 0 plus half, h is 0.5. So 0 plus half times 0.5 is 0.25. And for y value, it is y0. So y0 is 2 plus half k1. So k1 is negative 3. H is 0.5. So 2 plus half times negative 3 times 0.5 is 1.25. Okay, so K2 value is just the f of 0.25 and 1.25. So you just substitute 0.25 and 1.25 into our fxy. So exponent negative 0.25 minus 2 times 1.25. And the answer is negative 1.7212. Okay, next, K3 equals to f of x0 plus half h, comma y0 plus half k2h. So f of, alright, now x0 is 0 plus half h 0.5. Okay, so this one also 0.25. And for the y value, y0 is 2 plus half k2. K2 is this value here. So negative 1.7212. And h is 0.5. So after you calculate the value, the answer is 1.5697. Okay, so to find the K3 value, you just find f of 0.25, 1.5697. So it is exponent of negative 0.25 minus 2 times 1.5697. And the answer for K3 is negative 2.3606. Okay, and lastly for K4, the formula is given by f of x0 plus h, comma y0 plus k3h. So it is f of this one 0 plus 0.5, so f of 0.5, and y0 is 2 plus k3. K3 is this value here, negative 2.3606 times h also 0.5, and y value is 0.8197. So to find the K4 value, you just find the value of f of 0.5, 0.8197. You just substitute 0.5 and 0.8197 into our fxy function. So it is exponent negative 0.5 minus 2 times 0.8197. And the final answer for K4 is negative 1.0329. Okay, since we already got our K's value, so we can find the y1 value. So y1 equals to y0. So our y0 is 2 plus h over 6, 0.5 over 6, times with